Hi, this is a short video on common drain. This is by request from Mohammed from West Virginia University. He's taking a analog design class. Anyway, he requested I make a video on how to analyze these two. Basically, it's a common drain, or actually it's a common source. Okay. Source, and we have on this first circuit we have two ends. We have an end here and we have an end here. And what you want to look is that, or notice is that you have the gate connected to the drain. So this is what I call, or some people call, as diode connected MOSFET. Okay. And then in this second configuration, oh, by the way, this is an active load, as this as well is an active load. Okay, except that this one's a P channel, but it's not connected as a diode. Okay, so there's a little bit of differences. How do you treat this? Okay, now before I analyze these, let's back up a little bit and let's go just to a fundamental, and let's say we have a regular N channel with no resistor and the source, just a regular, and instead let's put a resistor and we'll call it RD. Okay, so this would be your VN, input signal, and this node would be your output. This would be your drain, source, and a gate. Okay, so how do you find your voltage gain? Basically your V out versus VN. Okay, well, you do a little signal, small signal analysis. Okay, and basically it should look like this. This should be your VGS, and then this is your current source, and this should be GM VGS, and this should be your positive side of the VGS and negative side of the VGS. That goes to ground, that goes to ground, VN, and let me label this. This is your gate, source, and your drain. Okay, now what we do is, oh, and let me go ahead and add R out. This would be the output impedance of the MOSFET. Okay, and then what we do is we add RD. Okay, now realize that the current is flowing in this direction, flows down the source. It cannot flow in this direction. Nope, can't flow in that direction. Okay, so then that current is going to flow back up. Okay, and since it flows back up, that goes positive, that goes negative. Okay, so this drain is actually V out. Okay, so now you're ready to do your gain analysis, and basically should be should be first define your gate, your VGS, and if you notice the VGS or the gate G is connected to VN, and then the ground is connected to source, so VGS is really VN. Okay. Now you can write an expression for V out. Okay. V out is going to be this voltage, right? And that's going to be your GM VGS. Basically, this current is going to flow through here, and it's going to flow through there, through these. Okay. And you can do a little simplification. Let's see. Let's go ahead and make a little simplification. Since I had it connected to ground there, this may be a little bit more intuitive. And that R out is actually connected in parallel with RD. Okay. So now you can write that it's a negative because there's an inversion. And it's going to be the GM times R out in parallel with RD. Okay. And that's going to be VN. Remember, this was this term is the current, right? That's GM, and this is your VGS. And since VGS is VN, plug in there. So that's the gain. Okay. So why am I doing this? Well, because you treat these two basically the same way. Okay. And if you look at one of the previous video, the video that I made about diode connected transistors or MOSFETs, when you look into the source, you should always think that it's 1 over GM. Okay, we'll go ahead and say that this is MOSFET 1 and this is MOSFET 2. And let me go ahead and put MOSFET M1 and M1 and M2. So we'll say that this the impedance looking into the source of M2 is 1 over GM2. Okay. So in a way, this is exactly like this. It's like a resistor. Okay. Except that it looks like that. Okay. So if you do the same procedure, okay, VGS there's going to be a R out because of the 1 of the first transistor. Okay, and since you're looking into here, it's 1 over GM two, and there's actually a R out, so you can also add that as well. Okay, so now it's pretty straightforward. V out is supposed to be GM1 and it's supposed to be R out 1 in parallel with R out 2 in parallel with 1 GM over 2. And that's the gain for that one. Okay. Okay, on this one, it's a little bit different in that This is a P channel. So you have your, let me see where, oh, here it is. Okay, so this is actually the source. That's the gate. This is the drain. So what you want to do is you want to look at the impedance, and you typically put Z, meaning impedance. So you're looking at the impedance, looking into the drain of that. Okay, and anytime you look into the impedance of the drain, whether it's the P channel or the AND channel, you have to realize that there's a R out associated with that. In this case, it would be R out P. Okay, and if you look at the impedance looking into the AND channel, there's also a R out N. Okay, so the equation for that is very similar. It's the same form. It'd be V out minus, and we'll say it's GM1. I'll say that this is MOSFET 1, and this we'll say is MOSFET 2. Okay, and it's going to be the parallel combination of the N, R out N, and parallel with R out P. Okay, so very simple. Don't have to derive too much. As long as you have this basic concept, you should be able to plug in whether it's a diode connected or a true active device with a P channel. Okay, hopefully that will help out those that are doing some circuit analysis and small signal. So this is one of the ways of deriving the voltage gain. Thank you for watching.